Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're standing at the edge of something so incomprehensibly vast that your brain is going to do that little glitch it does when you try to picture infinity. You know the one. That soft static behind your eyes, like a computer loading screen that never quite resolves. Because tonight, we are talking about the biggest galaxy humanity has ever discovered, and I need you to understand something right now. The numbers we're about to encounter do not behave the way numbers are supposed to behave. They don't fit on whiteboards, they don't fit in analogies, they barely fit in the observable universe. You're about to learn about a structure so enormous that if you try to cross it at the speed of light, the fastest anything can travel in this universe, you would die of old age approximately 160,000 times over. So, you probably won't survive this one, but at least you'll sleep well trying. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And hey, while you're settling in, drop a comment and let me know where you're listening from tonight and what time it is where you are. I always love reading those. Someone's always awake at 3 in the morning in Sao Paulo, or half asleep in a hammock in Melbourne, or tucked into a futon in Kyoto. Wherever you are, you're welcome here. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start, as you always do, by looking up. Maybe it's a clear night where you are, maybe it's not. It doesn't matter. Close your eyes if you want, or leave them half open, and just imagine a sky so dark and so deep that every pinprick of light is a sun. Thousands of them scattered like salt across black velvet. You've been told since childhood that those lights are stars, and that's true. But tonight you need to understand something bigger. Something almost rude in its scale. Every single one of those stars you can see with your naked eye belongs to just one galaxy. Yours, the Milky Way. And the Milky Way, bless its heart, is not particularly special. It's a perfectly respectable spiral galaxy, sure. 100,000 light years across, give or take. Home to somewhere between 100 billion and 400 billion stars, depending on which astronomer you ask and how generous they're feeling that day. It has nice spiral arms and a decent supermassive black hole at its centre, and it even has a cute little name that sounds like a candy bar. But in the grand catalogue of galaxies, the Milky Way is, well, mid. It's the Honda Civic of galaxies. Reliable, common, gets the job done. Nobody's writing poetry about it at cosmic dinner parties, and that's fine. That's actually the point tonight. Because you need a baseline. You need to feel the size of your own galaxy in your bones before we start talking about the ones that make it look like a crumb on a tablecloth. The Milky Way is your ruler, your yardstick, your "this is what normal looks like" reference card. And over the next little while, you're going to watch that ruler shrink. It's going to go from feeling impossibly large to almost comically small, like finding out your childhood home is actually a studio apartment compared to the mansions down the road. And that journey, that slow, bewildering deflation of scale, is one of the most genuinely humbling things a human brain can experience. Astronomers in the early 20th century didn't even know other galaxies existed. That's a mainstream historical fact that still lands like a punch. In 1920, the prevailing scientific consensus was that the Milky Way was the entire universe. Everything. The whole show. The complete cosmic inventory. There was a famous debate that year, the Great Debate they called it, between two astronomers named Harlow Shapley and Heber Curtis, and they stood in front of the National Academy of Sciences in Washington and argued about whether those fuzzy little smudges in the sky were clouds of gas inside our galaxy, or entire separate galaxies far, far away. Shapley said they were local, Curtis said they were distant, and for a while, nobody could prove either one right. The audience sat there in their wooden chairs, probably uncomfortable, listening to two men politely disagree about the size of everything. Scholars still argue whether the Great Debate actually changed many minds at the time, or whether it was more of a polite intellectual stalemate that history later romanticised. Some historians think the real shift didn't happen until a few years later, when Edwin Hubble pointed the 100-inch Hooker telescope at the Andromeda Nebula and found individual stars inside it, Cepheid variable stars whose pulsing brightness told him Andromeda was far too distant to be part of the Milky Way. That was the moment the universe cracked open. One galaxy became billions, and suddenly the Milky Way wasn't the ocean. It was a single droplet, a quirky little footnote from that era. Before Hubble's discovery, some astronomers genuinely referred to other galaxies as island universes, a term borrowed from the philosopher Immanuel Kant, who had speculated about their existence back in 1755. Kant, the same man who wrote dense, nearly unreadable treatises on the nature of morality and pure reason, apparently also had time to casually predict the existence of galaxies over a century before anyone could prove it. Philosophers, honestly, always showing up early to the party and then pretending they weren't even trying. So here you are, lying in the dark, and you now understand two things. One, your galaxy is enormous by human standards and hilariously average by cosmic standards. And two, humanity spent most of its intellectual history not even knowing other galaxies existed. You're already further along than almost every scientist who ever lived before 1925. Congratulations. Now let that thought settle into your pillow like a warm, heavy stone, because the next place we're going is deeper into the system that lets astronomers sort these galaxies into families and categories, a system dreamed up with tuning forks and telescopes and a surprising amount of artistic flair. The system you need to know about was born in the mind of Edwin Hubble, that same telescope-pointing, universe-expanding astronomer who ruined everyone's cozy one-galaxy worldview. After proving that other galaxies existed, Hubble did what any good scientist does when confronted with an overwhelming number of new things. He started sorting them. You know the impulse. It's the same one that makes you organise your bookshelf by colour or your phone apps by category. When the universe hands you billions of galaxies, you reach for a filing cabinet. Hubble's filing cabinet was shaped like a tuning fork. He published it in 1926, and astronomers still use a version of it today, which is either a testament to its elegance or a sign that nobody's come up with anything better in a century. The Hubble sequence, as it's called, divides galaxies into three main types. On the left side of the tuning fork you have elliptical galaxies, which look like smooth, glowing blobs ranging from nearly spherical to elongated like a rugby ball. Hubble labelled them E0 through E7, with the number indicating how stretched out they appear. On the right side, the fork splits into two prongs. The top prong holds normal spiral galaxies, the kind with graceful curving arms, and the bottom prong holds barred spiral galaxies, which have a thick bar of stars running through their centre before the arms begin. Sitting right at the junction between the ellipticals and the spirals are lenticular galaxies, which look like spirals that forgot to grow arms. They have a disc shape, but none of the dramatic swirling structure. They're the quiet middle children of the galactic family. Now, here's where it gets interesting for tonight's purposes. When Hubble first drew this diagram, he placed the ellipticals on the left and the spirals on the right, and he speculated that galaxies might evolve from left to right, starting as featureless blobs and gradually developing spiral arms as they aged. He called the ellipticals early-type galaxies and the spirals late-type galaxies. This turned out to be completely wrong. Galaxies do not evolve from elliptical to spiral. If anything, the opposite is closer to the truth. Spiral galaxies can merge together and lose their structure, eventually becoming elliptical. But the terminology stuck. To this day, astronomers still refer to elliptical galaxies as early type, even though they know the label is misleading. It's one of those charming little fossils of scientific history, like how we still call tinfoil, even though it's been made of aluminum for over 100 years. A quirky detail about Hubble's classification that most people never hear. He originally had a category for irregular galaxies too, the ones that didn't fit neatly into any shape, but he treated them almost as an afterthought, a cosmic junk drawer for the misfits. Some of those so-called irregulars turned out to be among the most fascinating objects in the sky. Galaxies caught mid-collision, galaxies being torn apart by gravity, galaxies doing things no tuning fork could predict. The universe, it turns out, doesn't care much about your filing system. What matters for you right now, as you settle deeper into your pillow, is understanding the elliptical branch of that fork, because that's where the monsters live. Spiral galaxies like the Milky Way are beautiful and photogenic, sure, but they tend to be modest in size. The largest spirals top out at maybe 200,000 light-years across. That's big by everyday standards, but practically petite compared to what elliptical galaxies can achieve. Ellipticals are the sumo wrestlers of the cosmos. They are massive, ancient, and they got that way by consuming everything around them. The very biggest elliptical galaxies sit at the centres of galaxy clusters, surrounded by hundreds or thousands of smaller galaxies, and over billions of years they have been slowly, patiently, swallowing their neighbours one by one. Astronomers call them brightest cluster galaxies, or BCGs, and they are the undisputed heavyweight champions of galactic size. Scholars still argue whether these giant ellipticals grow primarily through major mergers, where two similarly sized galaxies collide and fuse, or through minor mergers, where a big galaxy gradually absorbs many smaller companions like a whale filtering krill. The answer is probably both, in varying proportions, but the debate over which mechanism dominates is still very much alive in the astrophysical literature. It's one of those questions that sounds simple but requires extraordinarily difficult simulations and observations to answer. There's a mainstream historical fact here that often surprises people. The first known photograph of a galaxy other than our own was taken in 1888 by Isaac Roberts, a Welsh engineer turned amateur astronomer who captured an image of the Andromeda Nebula from his private observatory in Sussex. He thought he was photographing a solar system being born, a swirling disk of gas and dust condensing into planets. He had no idea he was looking at an entirely separate galaxy containing 1 trillion stars. The image is haunting when you see it, a faint blurry spiral emerging from the photographic emulsion, like a ghost trying to introduce itself. Roberts died in 1904, 2 decades before Hubble proved what Andromeda really was. He never knew what he'd captured. You lie there thinking about that, about how every generation of astronomers has looked at the same sky and seen something completely different. About how the categories we invent, elliptical, spiral, irregular, are just human attempts to impose order on something that resists order at every turn. The tuning fork is a useful map, but the territory it describes is wild and strange and full of exceptions. And the biggest exception of all, the galaxy so enormous it breaks the scale of Hubble's tidy diagram, is waiting for you further down this road. You're not there yet. You need to understand a few more things first, like exactly how big your own galaxy really is, not in vague hand-wavy terms, but in the kind of specific, slightly dizzying detail that makes the comparison to the giants actually land. Because 100,000 light-years is a number you've heard before, and it's probably lost its punch. So you need to feel it again, fresh, like the first time someone told you, and your jaw went a little slack. A light year sounds like it should be a measurement of time. It has the word year right there in the name, and your brain latches onto that familiar unit and tries to make sense of it. But a light year is a measurement of distance, and it is a preposterous one. It's the distance that light travels in 1 year, moving at roughly 300,000 kilometers per second, not per hour, per second. In the time it took you to read that last sentence, light travelled far enough to circle the Earth about 7 times, and a single light year is the distance light covers doing that non-stop for an entire year. That works out to about 9.5 trillion kilometres, 9.5 trillion. You can say the number, but you can't feel it. Nobody can. The human brain evolved to judge distances like, that tree is closer than that rock, and the watering hole is a day's walk east. It did not evolve to comprehend trillions of anything. So when someone tells you the Milky Way is 100,000 light years across, what they're really saying is that if you turned on a flashlight at one edge of the galaxy and aimed it at the other edge, the beam would arrive 100,000 years later. 100,000 years. That's roughly the entire span of modern human existence. Homo sapiens have been walking around on this planet for about 300,000 years, give or take, and for a beam of light to cross your galaxy would eat up a third of that history. Every empire that ever rose and fell, every language that was invented and forgotten, every war and every love song and every single episode of every television show ever made, all of it fits comfortably inside the time it takes light to commute across the Milky Way. And light, remember, is the fastest thing there is. Nothing in the universe moves quicker. If you tried to make that same crossing in, say, the fastest spacecraft humanity has ever built, the Parker Solar Probe, which tops out at about 690,000 kilometers per hour, the trip would take you roughly 160 million years. You would not pack enough snacks. But the Milky Way isn't just wide, it has depth, structure, neighbourhoods. You live in one of the spiral arms, a minor one called the Orion Arm, sometimes called the Orion Spur, because astronomers apparently couldn't decide whether it deserved full arm status or just spur status. Scholars still argue about the exact structure of the Milky Way's arms actually, because mapping the inside of a galaxy while you're sitting inside it is a bit like trying to draw a map of your house while locked in the bathroom. You can infer a lot, but you're always guessing about the rooms you can't see. Current estimates suggest the Milky Way has 4 major spiral arms winding out from a central bar, with several smaller spurs and branches in between, but the precise count and arrangement shift every time someone publishes a new survey. The centre of the galaxy is roughly 26,000 light years from where you're lying right now. If you could somehow look directly at it, which you can't because there's too much interstellar dust in the way, you'd be staring at a region called Sagittarius A, home to a supermassive black hole with the mass of about 4 million suns. 4 million suns packed into a space smaller than the orbit of Mercury. That black hole is the anchor around which the entire galaxy slowly revolves, and your solar system takes about 230 million years to complete one full orbit. Dinosaurs were just getting started last time Earth was in this part of the galactic neighbourhood. That orbital period is sometimes called a galactic year, and in the entire history of the solar system, only about 20 galactic years have passed. The solar system is roughly 20 galactic years old. You can hold that number in your head, 20. It almost sounds manageable until you remember what each one of those years contains. A mainstream historical fact that grounds this nicely. The first serious attempt to measure the size of the Milky Way was made by William Herschel in the late 1700s. Herschel, the same man who discovered Uranus and built the largest telescopes of his era, tried to map the galaxy by counting stars in different directions and assuming they were evenly distributed. His model looked like a lumpy, irregular cloud with the sun sitting almost exactly at the centre. He was wrong about the centre part. We now know the sun is way out in the suburbs, not downtown at all. But Herschel's method was clever for its time, and it established the basic principle that you can learn about the shape of something enormous by carefully sampling its contents. A quirky footnote about Herschel. His sister Caroline was a formidable astronomer in her own right, discovering 8 comets and several nebulae while also serving as William's tireless assistant. She was the first woman to receive a salary for scientific work in England, and she lived to 97, which in the 1700s was basically immortality. The Milky Way also has a halo, a vast, roughly spherical region of thinly scattered stars, ancient globular clusters, and dark matter that extends well beyond the visible disk. If you include the halo, the Milky Way's total diameter might stretch to nearly 2 million light-years, though the vast majority of that space is almost unimaginably empty. It's like saying your property extends to the fence line even though your actual house only occupies a tiny patch in the middle. The dark matter halo is invisible, detectable only through its gravitational influence, and it contains several times more mass than all the visible stars combined. You are, in a very real sense, living inside a structure whose true size and mass are dominated by something you cannot see, cannot touch, and barely understand. That thought alone is worth a slow exhale. So there it is, your galaxy, your home. 100,000 light-years of disk, 400 billion stars, a dark matter cocoon stretching far beyond the edges, and one mildly embarrassed sun tucked away in a minor arm. It's magnificent by any human standard, and it is about to become very, very small. The thing about elliptical galaxies is that they don't try to impress you with elegance. Spiral galaxies are the peacocks of the cosmos, all sweeping arms and dramatic dust lanes and photogenic blue, star-forming regions that look fantastic on the cover of a textbook. Elliptical galaxies, by contrast, look like someone smudged a thumbprint on the sky. They're smooth, featureless, and often tinged a dull yellow or reddish hue, like a sunset that gave up halfway through. If spiral galaxies are the flashy sports cars of the universe, elliptical galaxies are the enormous, slightly beige warehouses on the outskirts of town. Nobody photographs them for fun, but those warehouses are full of stuff, more stuff than you'd believe. Elliptical galaxies range wildly in size. The smallest ones, called dwarf ellipticals, can be just a few thousand light-years across, and contain only a few billion stars, which sounds like a lot until you remember that the Milky Way has hundreds of billions. These dwarfs are the runts, the cosmic hamsters, easily overlooked and often found orbiting larger galaxies like nervous attendants. But at the other end of the spectrum, elliptical galaxies can grow to sizes that make spiral galaxies look like garnishes on a dinner plate. The largest ellipticals, the ones sitting fat and satisfied at the centres of massive galaxy clusters, can span millions of light-years and contain trillions of stars. Trillions, not billions, trillions. That's the kind of number that makes your brain quietly file a complaint with management and request a transfer to a simpler universe. What makes elliptical galaxies so different from spirals isn't just their shape, it's their personality, if you'll forgive the anthropomorphism. Spiral galaxies are active. They're still making new stars, still churning through vast reserves of gas and dust, still cooking up fresh blue giants in their arms. They're alive in the most literal astrophysical sense. Elliptical galaxies, especially the big ones, are mostly done. They've used up or expelled most of their gas. Star formation has slowed to a trickle or stopped entirely. The stars that remain are old, red, and cool, like embers in a fireplace that burned through its wood hours ago. Walking through a giant elliptical galaxy would be like wandering through an enormous, dim retirement community where everything is very clean and very quiet and nobody has thrown a party in 6 billion years. This isn't to say elliptical galaxies are boring. They're not. They're fascinating precisely because of what they represent, the end state of galactic evolution, or at least one possible end state. Scholars still argue about whether all galaxies eventually become elliptical, or whether some spirals managed to avoid that fate by steering clear of major collisions. The prevailing view is that when two large spiral galaxies collide and merge, the collision disrupts their orderly rotation, scatters their stars into random orbits, and produces a galaxy that has no disk, no arms, no particular structure at all. Just a smooth, puffy ball of stars orbiting in every conceivable direction. The process takes hundreds of millions of years, and if you could watch it in fast forward, it would look like two elegant pinwheels crashing into each other and producing a cotton ball. A very large, very heavy cotton ball. A mainstream historical fact that enriches this picture. The classification of elliptical galaxies was refined significantly in the 1970s and 80s by astronomers who realized that not all ellipticals are created equal. Some are genuinely spherical, supported by the random motions of their stars, like a swarm of bees buzzing in all directions. Others are flattened not because they're spinning like a disk, but because of an anisotropy in their stellar orbits, a lopsidedness in how the stars move that creates an elongated shape without any organized rotation. This distinction between pressure-supported and anisotropic ellipticals was a subtle but important advance, and it came from painstaking spectroscopic observations that measured how fast stars were moving in different parts of the galaxy. The universe never gives up its secrets easily. You always have to measure something tedious and then argue about what it means. A quirky detail that rarely makes it into popular accounts. Some elliptical galaxies have faint shells or ripples in their outer regions, delicate concentric arcs of starlight that look like the rings you see when you drop a pebble into still water. These shells are the fossil evidence of past mergers. When a smaller galaxy falls into a larger one, its stars get stripped away and pile up at certain radii, creating these ghostly ripples that can persist for billions of years. They're incredibly faint and hard to detect, but when you see them in deep images, they're haunting. Each shell is a gravestone marking a galaxy that used to exist independently and now exists only as a subtle architectural feature in something much larger. You absorb that for a moment, the idea that galaxies can be swallowed so completely that the only trace of their existence is a faint ripple in someone else's glow. The giant elliptical galaxies, the ones we're building toward tonight, sit at the very top of this food chain. They're the galaxies that ate everything. Over billions of years, they've consumed dozens, maybe hundreds of smaller galaxies, growing ever larger and ever more massive with each meal. They tend to live at the centers of galaxy clusters, surrounded by their remaining uneaten neighbors, and they often have extremely powerful active galactic nuclei, supermassive black holes at their cores that are busily feasting on infalling gas and radiating energy across the electromagnetic spectrum. These are the empires of the universe. They didn't get big by being creative or dynamic. They got big by being patient and hungry and occupying the most gravitationally privileged real estate in their neighborhood. You can almost admire the strategy in a cold, Darwinian sort of way. Sit in the middle, wait, eat whatever drifts too close, repeat for 10 billion years, and somewhere out there, in a galaxy cluster over 1 billion light years from your pillow, one of these patient, bloated empires grew to a size that made astronomers double-check their instruments and then check them again. You need to understand how galaxies eat each other, because without that, the sheer size of the giants waiting ahead will feel like a magic trick rather than a process, and it is a process. A slow, gravitational, almost lazy process that has been unfolding since the first galaxies formed over 13 billion years ago. Nothing about galactic cannibalism is fast. Nothing about it is dramatic in the way a Hollywood explosion is dramatic. It's more like watching two clouds merge on a summer afternoon, except each cloud contains 100 billion stars, and the afternoon lasts 1 billion years. It starts with gravity. Everything in the universe pulls on everything else, and galaxies are no exception. When two galaxies drift close enough to each other, their mutual gravitational attraction begins to distort them. Long, thin streamers of stars get pulled outward, stretching like taffy toward the approaching neighbour. These streamers are called tidal tails, and they're some of the most visually striking features in all of astronomy. The antenna galaxies, a famous pair of colliding spirals about 60 million light-years away, have tidal tails that stretch hundreds of thousands of light-years into space. Impossibly delicate ribbons of stars flung outward by the gravitational tug-of-war between two galaxies that are in the process of becoming one. If you've ever seen a photograph of them, you know they look less like a collision and more like a dance. Two partners spinning, arms extended, fingers trailing through the dark. But here's the thing that surprises most people when they first learn about galaxy mergers. The stars almost never actually hit each other. When two galaxies collide, the individual stars inside them are so far apart relative to their size that they pass right through each other like two swarms of gnats merging in a park. If you shrank the sun down to the size of a grain of sand, the nearest other grain of sand representing the closest neighbouring star would be about 4 miles away. The space between stars is staggeringly, absurdly empty. So when galaxies merge, the stars rearrange themselves gravitationally, trading orbits and shuffling into new configurations, but they almost never physically collide. It's a collision without any collisions. The gas and dust between the stars, however, does collide quite violently, and these gas collisions trigger enormous bursts of new star formation. Merging galaxies often light up with brilliant blue knots of newborn stars, temporary fireworks celebrating the union of two formerly separate systems. A mainstream historical fact worth noting here: the first person to propose that galaxies could interact gravitationally was the Swedish astronomer Erik Holmberg, who in 1941 performed an ingenious experiment using light bulbs. He couldn't simulate gravity with computers because computers capable of that wouldn't exist for decades. So instead, he arranged light bulbs on a table to represent stars, used their combined light intensity as a proxy for gravitational force, and measured how two model galaxies would distort each other during a close encounter. He used photocells to measure the gravitational pull of light at various points between his bulb galaxies. It was brilliantly creative and shockingly accurate. His results predicted tidal tails and bridges between interacting galaxies long before any were observed. Holmberg essentially discovered galactic cannibalism with desk lamps and a light meter, which is the kind of resourcefulness that makes you want to sit down and rethink every excuse you've ever made about not having the right tools. Scholars still argue about the precise mechanics of how mergers transform galaxy morphology. The basic picture is well established. When two disk galaxies of roughly equal size merge, their organised rotational motion gets disrupted, and the result is an elliptical galaxy whose stars orbit chaotically in all directions. This is called a major merger, and it's the primary mechanism for building the biggest elliptical galaxies. But the details are devilishly complicated. How much gas is involved? At what angle do the galaxies approach each other? How fast are they moving when they first interact? How massive is the dark matter halo surrounding each one? Every one of these variables changes the outcome, and simulating even a single merger accurately requires supercomputers running for weeks. The universe performed billions of these mergers simultaneously, without a single line of code, which is either humbling or infuriating depending on your relationship with technology. There are also minor mergers, where a large galaxy absorbs a much smaller companion. These are less dramatic but far more common, and over cosmic time, they add up. A giant elliptical galaxy at the centre of a cluster might experience dozens or even hundreds of minor mergers over its lifetime, each one adding a little more mass, a few more billion stars, gradually inflating the galaxy like a balloon being blown up one tiny breath at a time. The evidence for this is written in the outskirts of these galaxies, where you can sometimes detect stellar streams, faint trails of stars that trace the orbits of galaxies that were recently absorbed. These streams are the breadcrumbs left behind by the eaten. They circle the host galaxy like ghostly ribbons, slowly dispersing over millions of years until they become indistinguishable from the galaxy's own stellar population. Remember those shells and ripples from earlier? Same idea, different geometry. The universe keeps a record of every meal, if you know where to look. A quirky detail that astrophysicists find endlessly entertaining. During a major merger, the two supermassive black holes at the centres of the colliding galaxies will eventually sink toward each other and merge as well. But this process takes an extraordinarily long time, and there's a theoretical bottleneck called the final parsec problem, where the two black holes get close enough to orbit each other but can't quite lose enough energy to spiral inward and merge. They get stuck, like two people trying to merge into the same lane on a highway, neither one willing to yield. Some simulations suggest they can remain in this awkward orbital standoff for billions of years. How they eventually merge is still an active area of research, and the gravitational waves produced when they finally do are among the strongest signals in the universe, rippling through the fabric of space-time itself. You are building the recipe now: gravity, time, patience, and a willingness to consume your neighbours without remorse. That's how you make a giant galaxy. And the one you're heading toward next didn't just follow this recipe, it perfected it. You arrive at IC1101 the way you arrive at anything truly enormous, gradually, and then all at once. For decades, this was the galaxy that held the crown, the biggest, the most massive, the one that astronomers pointed to when someone asked what happens when galactic cannibalism goes completely, magnificently overboard. And even though its reign has been complicated by newer discoveries, which you'll get to soon enough, IC1101 remains one of the most staggering objects in the observable universe. It deserves your full attention, and tonight, lying in the dark with your eyes half closed, you're going to give it exactly that. IC1101 sits at the centre of a galaxy cluster called Abell 2029, roughly 1 billion light-years from Earth. 1 billion. That means the light reaching your telescopes tonight left IC1101 when life on Earth was still exclusively single-celled. Multicellular organisms hadn't been invented yet. Nothing had eyes, nothing had bones, nothing had opinions about anything. And all that time, that light was silently crossing the void, passing through expanding space, redshifting slowly toward longer wavelengths, carrying with it the image of a galaxy so large that, when astronomers first calculated its diameter, some of them genuinely thought there had been a mistake. The commonly cited figure is that IC1101 is roughly 6 million light-years in diameter. 6 million. Compare that to the Milky Way's 100,000 and you start to see the problem. IC1101 is approximately 60 times wider than your entire galaxy. If the Milky Way were the size of a dinner plate, IC1101 would be the size of a modest backyard swimming pool. You could fit dozens of Milky Ways inside it without any of them touching the edges. Some estimates are more conservative, placing the diameter at closer to 4 million light-years, and others have pushed it even higher, depending on where you define the galaxy's boundary and what wavelength of light you're using to trace it. But even the most cautious measurements put IC1101 in a class so far beyond normal galaxies that the comparison barely functions. It's like comparing a rowboat to an aircraft carrier, and then realizing the aircraft carrier is also somehow the size of a small country. IC1101 was first catalogued in 1890 by the astronomer John Louis Emile Dreyer, who included it in his Index Catalogue, a supplement to the earlier New General Catalogue of Deep Sky Objects. Dreyer was a Danish-Irish astronomer working at Armagh Observatory in Northern Ireland, and his catalogues were essentially enormous handwritten lists of fuzzy things he and others had spotted through telescopes. He had no idea what IC1101 was. To him, it was just another faint smudge, one of thousands, assigned a number and filed away. The fact that this particular smudge turned out to be the largest known galaxy in the universe is the kind of cosmic irony that makes you want to pat Dreyer on the shoulder and say, "You have no idea what you just wrote down." That's a mainstream historical fact that carries a certain weight. The biggest galaxy ever catalogued was first recorded as a footnote in a supplementary list by a man who thought he was just being thorough. The galaxy cluster surrounding IC1101, Abell 2029, is itself an impressive beast. It contains hundreds of galaxies, all bound together by gravity, all orbiting within a vast cloud of superheated gas that radiates powerfully in X-rays. The cluster's total mass is estimated at over 100 trillion times the mass of the Sun, and most of that mass is dark matter, the invisible scaffolding that holds the whole structure together. IC1101 sits at the gravitational centre of all of this, the heaviest object in the densest part of the cluster, like a boulder resting at the bottom of a valley. Everything falls toward it. Everything feeds it. The cluster is IC1101's pantry, and it has been helping itself for billions of years. Scholars still argue about exactly how IC1101 grew to its current size. The dominant theory is that it formed through a long series of mergers, both major and minor, consuming galaxy after galaxy over cosmic time. Some models suggest it may have undergone a particularly violent period of merging activity several billion years ago, when the cluster was younger and more dynamically active, with galaxies buzzing around more chaotically and colliding more frequently. Other models suggest a more gradual accumulation, a steady drip of small galaxies falling inward and being absorbed without much fanfare. The truth is probably somewhere in between, a combination of spectacular collisions and quiet snacking, but the precise merger history of IC1101 is not something anyone can reconstruct with certainty. The fossil evidence, the shells, streams, and kinematic signatures buried in the galaxy's stellar populations is there, but reading it is like trying to reconstruct a meal from crumbs left on a tablecloth that hasn't been changed in 5 billion years. A quirky detail about Abell 2029, the hot gas filling the cluster, called the intracluster medium, has a temperature of roughly 100 million degrees. That's hotter than the centre of the Sun. You might wonder how gas that hot doesn't just blow everything apart, and the answer is that the cluster's enormous gravitational pull holds it in place. The gas is trapped, glowing furiously in X-rays but unable to escape. If you could somehow fly through Abell 2029, which you absolutely could not because you'd be vaporized in a microsecond, you'd be swimming through a fog of plasma so thin it makes the best laboratory vacuum on Earth look crowded. It's hot but sparse, a burning emptiness. And somewhere in the middle of that burning emptiness, IC1101 sits like an ancient emperor on a throne made of gravity, patient and colossal, and completely indifferent to the fact that anything as small as you exists at all. You breathe out slowly and let the image settle. 6 million light years across, a galaxy so big that light itself needs 6 million years to get from one side to the other. You'll carry that number with you as we go forward, because soon you're going to learn why even that number might not be entirely trustworthy. The problem with measuring a galaxy is that galaxies don't have edges. This sounds like it should be a minor technical detail, the kind of thing astronomers sort out over coffee and then move on from. But it's not minor at all. It's one of the fundamental challenges of extragalactic astronomy, and it directly affects every size estimate you've heard tonight, including that jaw-dropping 6 million light-year figure for IC1101. So before you take any of these numbers at face value, you need to understand why measuring the size of a galaxy is more like measuring the size of a cloud than measuring the size of a building. Buildings have walls, clouds just sort of fade away. When you look at a galaxy through a telescope, what you see is light. Stars emit light, gas emits light, dust sometimes glows in infrared. The centre of a galaxy is bright because stars are packed tightly together. As you move outward from the centre, the density of stars decreases, and so does the surface brightness, the amount of light coming from each patch of sky. At some point, the galaxy gets so faint that it blends into the background glow of the sky itself, and you can't tell where the galaxy ends and the darkness begins. That boundary isn't sharp, it's a gradient. The galaxy doesn't stop, it just becomes undetectable, and where you draw the line between still part of the galaxy and now you're looking at empty space depends entirely on how sensitive your telescope is, how long you expose your image, how carefully you subtract the background light, and what wavelength you're observing in. This is why galaxy sizes can vary so dramatically from one study to another. An astronomer using a relatively shallow survey might measure IC 1101 and report a diameter of 2 million light-years. Another astronomer using deeper imaging might trace the galaxy's faint outer envelope much further and report 4 million light-years. A third astronomer, using the deepest possible exposures and the most aggressive background subtraction, might push the boundary out to 6 million light-years or beyond. None of them are wrong exactly, they're just measuring different things. They're drawing the line at different levels of faintness. It's a bit like asking how big a campfire is. Are you measuring the flames, the area that feels warm, the farthest point where you can still smell smoke? All three are legitimate answers, and all three give you wildly different numbers. A mainstream historical fact that illustrates this beautifully. In the 1960s, astronomer Gérard de Vaucouleurs developed a mathematical profile to describe how the brightness of elliptical galaxies decreases with distance from the centre. His formula, known as the de Vaucouleurs profile or the r to the 1/4 law, showed that elliptical galaxies fade gradually according to a smooth mathematical curve that technically never reaches zero. The profile just keeps declining, getting fainter and fainter, asymptotically approaching zero brightness, but never actually arriving. In mathematical terms, this means an elliptical galaxy, described by de Vaucouleurs' law, has no definite edge at all. It extends infinitely, just getting dimmer and dimmer forever. In practice, of course, at some point the galaxy's outermost stars are so sparse and so faint that they're indistinguishable from the intergalactic background. But the mathematical model has no built-in cutoff. The galaxy is technically infinite in extent, which is a deeply unsatisfying answer if you're trying to quote a diameter. To deal with this, astronomers invented several conventions for defining galaxy size. One common approach is to measure the effective radius, which is the radius within which half of the galaxy's total light is contained. This is well defined and reproducible, but it tells you more about the galaxy's concentration than its actual extent. Another approach is to measure the isophotal radius, which is the radius at which the surface brightness drops below some chosen threshold, usually 25 magnitudes per square arcsecond in the B band. This is the most commonly quoted size of a galaxy, but it's explicitly dependent on the chosen threshold. Change the threshold and the galaxy gets bigger or smaller, like adjusting the volume knob on a radio. A third approach, popular for giant ellipticals, is to measure the extent of the diffuse stellar halo, the vast, dim cloud of stars that surrounds the main body of the galaxy. These halos can extend enormous distances, and they're where most of the disagreement about IC 1101 size comes from. Scholars still argue about whether the outermost parts of a brightest cluster galaxy, like IC 1101, should be considered part of the galaxy itself, or part of the intracluster light, a diffuse glow of stars that belong to the cluster as a whole, rather than to any individual galaxy. These orphaned stars were stripped from smaller galaxies during past mergers and now wander freely through the cluster's gravitational potential, not bound to any particular galaxy. Where IC1101 ends and the intracluster light begins is genuinely ambiguous. Some astronomers draw the boundary close to the galaxy's core and arrive at a diameter of 2 or 3 million light-years. Others include the full extended envelope and get 6 million or more. The galaxy itself doesn't care about the distinction. The stars don't know whose team they're on. A quirky wrinkle in all of this is that different wavelengths of light reveal different structures. Observe a galaxy in visible light and you see the stars. Observe it in radio wavelengths and you might see enormous jets and lobes of plasma extending far beyond the stellar body. Observe it in X-rays and you see the hot gas halo. Each wavelength tells a different story about the galaxy's size, and none of them is the complete story. A galaxy observed in radio waves can appear many times larger than the same galaxy observed in visible light, because the radio-emitting plasma can extend millions of light-years beyond the last star. This distinction is going to become extremely important very soon. When you encounter a galaxy whose radio structure dwarfs even IC1101's most generous size estimates. But for now, just hold on to this thought. Size, when it comes to galaxies, is not a single number. It's a conversation, and the answer depends on who's talking and what they're looking at. You let that complexity wash over you like warm water, understanding that the universe resists simple measurement even when measurement is all we have. Now that you understand how tricky it is to pin down where a galaxy ends, you can appreciate what it means when astronomers say IC1101 contains somewhere around 100 trillion stars. That number, 100 trillion, is an estimate wrapped in an assumption bundled inside a best guess. But even if it's off by a factor of 2 or 3, which it might be, the result is still staggering. 100 trillion is 1,000 times more stars than the Milky Way contains. 1,000 Milky Ways, stirred together and compressed into a single glowing mass. You could spend a lifetime counting one star per second, and you wouldn't finish cataloguing even a small percentage of what IC1101 holds before the sun itself burned out. The stars inside IC1101 are overwhelmingly old. This is one of the defining characteristics of giant elliptical galaxies, and it gives IC1101 its distinctive appearance. When you look at a spiral galaxy like the Milky Way, you see a mix of stellar ages and colours. Blue stars, which are young, hot and massive, blaze in the spiral arms alongside clouds of gas and dust, where new stars are still being born. Red and yellow stars, which are older and cooler, populate the central bulge and the spaces between the arms. The result is a galaxy that looks vibrant and variegated, full of contrast. IC1101, by contrast, glows with a uniform golden-amber hue, like a city seen through fog at dusk. Almost all of its stars are old red giants, and ancient low-mass stars that have been burning slowly and steadily for billions of years. The hot blue stars that would add colour and contrast burned out long ago, and new ones aren't being formed because the galaxy has used up or expelled virtually all of its star-forming gas. This gives IC1101 a certain melancholy beauty. It's a galaxy that has finished doing things. The construction crews have gone home, the scaffolding has been taken down. What remains is a vast, warm, quietly glowing monument to everything it once was, and everything it consumed to become what it is. If spiral galaxies are cities in their prime, buzzing with activity and construction cranes, giant ellipticals like IC1101 are ancient capitals long past their peak, still magnificent but running on memory and accumulated wealth rather than fresh industry. A mainstream historical fact that connects here. The study of stellar populations in galaxies was pioneered by Walter Baade during World War II. Baade, a German astronomer working at Mount Wilson Observatory in California, took advantage of the wartime blackout of Los Angeles to observe the Andromeda galaxy with unprecedented clarity. With the city lights extinguished by military order, the skies above Mount Wilson became dark enough for Bard to resolve individual stars in Andromeda's central bulge for the first time. He discovered that the stars in the bulge were fundamentally different from the stars in the spiral arms. The bulge stars were old, red, and metal-poor. The arm stars were young, blue, and metal-rich. He called these two groups Population 2 and Population 1, respectively, numbering them in the reverse of what you'd expect because the old stars were identified first. This classification system, born from a wartime blackout and a clear desert sky, remains foundational to how astronomers understand galaxies today. IC1101 is dominated almost entirely by Population 2 stars, the ancient ones, the cosmic elders. The mass of IC1101 is even more difficult to pin down than its size, but estimates place it somewhere around 100 trillion solar masses, give or take a generous margin. Some of that mass is in stars, some is in the remnants of dead stars, white dwarfs and neutron stars and stellar mass black holes scattered throughout the galaxy like seeds in a watermelon. A significant fraction is in hot gas, the thin but incredibly hot plasma that fills the space between stars and radiates in X-rays, and a very large portion, probably the majority, is in dark matter, the invisible gravitational scaffolding that holds the entire structure together. The dark matter halo of IC1101 is thought to extend well beyond the visible galaxy, forming an enormous invisible cocoon that might stretch tens of millions of light years in diameter. You can't see it, you can't touch it, but without it, IC1101 would fly apart, its stars scattering into the void like sparks from a bonfire. Scholars still argue about the exact ratio of dark matter to visible matter in galaxies like IC1101. The standard cosmological model predicts that dark matter should outweigh visible matter by roughly 5-to-1 across the universe, but individual galaxies can deviate significantly from this average. Some giant ellipticals appear to have even higher dark matter fractions, suggesting they've accumulated enormous dark matter halos through their long history of mergers. Others seem to have surprisingly little dark matter, at least in their central regions, which has led to some creative theoretical gymnastics. The field is very much alive, and every new observation adds a data point to a picture that is still frustratingly incomplete. A quirky detail about the colour of IC1101 that rarely gets mentioned. The golden amber glow of the galaxy is sometimes described in scientific papers as consistent with a stellar population that is roughly 10 to 12 billion years old. That means the average star in IC1101 formed when the universe itself was only a couple of billion years old. These stars have been shining since before the Earth existed, before the Sun existed, before the atoms that make up your body were assembled inside earlier generations of stars. When you look at IC1101, you are looking at light produced by stars that were already ancient when your solar system was just a collapsing cloud of gas and dust. There's something deeply calming about that. The idea that those distant amber points of light have been quietly burning for almost the entire history of the universe, patient and steady, asking nothing of anyone. You feel the weight of those 100 trillion stars pressing gently against your imagination, not crushing it, but stretching it, the way a deep breath stretches your lungs. And now your thoughts drift downward, toward the centre of this enormous golden haze, where something even more extraordinary is hiding in the dark. You descend toward the centre of IC1101 the way you might sink into a warm bath slowly, with a slight sense of surrender. The golden glow of 100 trillion stars surrounds you on all sides, but as you move inward, the stars grow denser, the light grows warmer, and the gravitational pull beneath you deepens like a bass note dropping below the range of human hearing. Something is waiting at the bottom of this galaxy, something that doesn't emit light, doesn't reflect light, and doesn't particularly care about light at all. It just sits there, impossibly heavy, bending the fabric of space-time around itself like a bowling ball on a trampoline, except the bowling ball weighs as much as a continent, and the trampoline is the actual structure of reality. The supermassive black hole at the centre of IC 1101 is estimated to be somewhere between 40 and 100 billion solar masses. Let that land for a moment. The supermassive black hole at the centre of the Milky Way, Sagittarius A star, is about 4 million solar masses, and that's already an object so dense that nothing, not light, not information, not your most optimistic prayers, can escape once it crosses the event horizon. IC 1101's central black hole is potentially 25,000 times more massive than that. It's in a category that astronomers sometimes informally call ultramassive, a term that didn't exist until they started finding black holes so large that supermassive felt like an understatement. It's like discovering a mountain so tall that enormous doesn't cover it, and you have to invent a new word that means, no, seriously, you don't understand. A mainstream historical fact grounds this. The existence of supermassive black holes at the centres of galaxies was first seriously proposed in the 1960s, when astronomers were trying to explain quasars, those bizarrely bright point sources of light that seem to be pouring out more energy than entire galaxies from a region smaller than the solar system. The theoretical physicist Edwin Salpeter and the astrophysicist Yakov Zeldovich independently suggested that quasars might be powered by accretion onto massive black holes, a process in which infalling matter converts gravitational energy into radiation with extraordinary efficiency. It took decades for this idea to gain widespread acceptance, and even longer for astronomers to confirm that essentially every large galaxy harbours a supermassive black hole at its centre. The relationship between a galaxy and its central black hole is now understood to be fundamental. They grow together, influence each other, and their masses are correlated in a way that suggests a deep symbiotic connection stretching back to the earliest epochs of galaxy formation. This correlation is called the M-sigma relation, and it's one of the most important empirical relationships in modern astrophysics. It says that the mass of a galaxy's central black hole is tightly correlated with the velocity dispersion of stars in the galaxy's bulge, which is essentially a measure of how fast the stars are buzzing around. Bigger bulge, faster stars, bigger black hole. The relationship holds across an enormous range of galaxy sizes, from relatively modest ellipticals to monsters like IC 1101, and it implies that the black hole and the galaxy regulate each other's growth through feedback mechanisms. When the black hole is actively feeding, it blasts energy outward in the form of radiation and jets, heating the surrounding gas and preventing it from cooling and forming new stars. When the gas supply dwindles, the black hole quiets down and the galaxy settles into a peaceful state. It's a cosmic thermostat cycling between active and dormant phases over billions of years. Scholars still argue about the exact physical mechanisms that establish and maintain the M-sigma relation. Some models emphasize the role of powerful jets and outflows from the black hole, which can sweep gas out of the galaxy entirely and shut down star formation across enormous volumes. Other models focus on radiative feedback, where the intense luminosity of an accreting black hole heats the surrounding gas enough to prevent it from collapsing into stars. Still others suggest that the correlation emerges naturally from the statistics of galaxy mergers, without any direct physical coupling between the black hole and the stars at all. The debate is sophisticated and ongoing, and it touches on some of the deepest questions in galaxy evolution. Now, what would it actually feel like to fall into a black hole this massive? The answer, surprisingly, is that it would feel like almost nothing, at least initially. The event horizon of an ultramassive black hole is so far from its centre that the tidal forces at the boundary, the stretching and compressing caused by differences in gravitational pull across your body, would be negligible. You would cross the event horizon without feeling a thing. No burning, no crushing, no dramatic special effects. You just drift past an invisible boundary beyond which no return is possible, and you might not even notice the moment it happened. This is profoundly different from falling into a small black hole, where the tidal forces would stretch you into a thin strand of atoms, a process cheerfully called spaghettification, long before you reach the event horizon. An ultra-massive black hole is so large that it kills you politely, with exquisite gentleness, giving you plenty of time to contemplate your situation before the interior geometry eventually tears you apart somewhere far inside. A quirky thought experiment that physicists enjoy. If you were falling into IC1101's central black hole, and you looked back toward the universe you were leaving behind, you would see time outside accelerating. Stars would be born and die in fast forward. Galaxies would spin and merge like time-lapse footage. The entire future history of the universe would compress into a flickering slideshow as you fell deeper, because from your frame of reference, time outside is speeding up relative to your own increasingly warped local time. You would, in principle, witness the end of the universe before the black hole's interior destroyed you. This is an idealized thought experiment, of course, and real physics near a singularity gets complicated in ways that general relativity alone can't fully describe. But the image is haunting. Falling forever inward, watching everything else rush toward its conclusion, alone and calm and weightless in the dark. You pull yourself back from the center of IC1101 gently, like waking from a dream that was becoming too vivid. The black hole recedes behind you, and the golden stars return, and you float upward through layers of ancient light toward the surface of this impossible galaxy. But something has shifted in your perspective now. You're beginning to wonder what it would be like to live here, to be born on a planet somewhere inside this colossal structure, looking up at a sky fundamentally different from your own. You pick a spot somewhere in the middle of IC1101, not too close to the center where the stellar density becomes overwhelming, and not too far out in the dim periphery where stars are sparse and lonely. You imagine a planet here, a rocky world orbiting a calm orange star that has been burning steadily for 9 billion years. The star is old and reliable, the kind of sun that doesn't throw tantrums, and the planet is temperate enough for liquid water, at least in this thought experiment. You step outside on a clear night and look up, and what you see is nothing like the sky you know from Earth. The first thing you notice is that there is no dark sky. Not really. The stellar density in the interior of a giant elliptical galaxy is so much higher than in the Milky Way's suburban spiral arm that the night sky would be a continuous soft golden glow. Not blindingly bright, not like daylight, but luminous in a way that eliminates true darkness. Imagine the sky on a clear night replaced by something closer to a perpetual twilight. A warm amber wash with no distinct constellations, no recognizable patterns, just a smooth gradient of light that brightens toward the galactic center and dims toward the outskirts. You might still see individual bright stars nearby, the way you can see individual streetlights in a well-lit city, but the background would never go fully black. The concept of a dark, star-scattered sky, the sky that inspired every mythology and every navigational system and every romantic evening in human history, simply wouldn't exist here. Darkness, on this planet would be a foreign concept. That thought is strange and a little sad, isn't it? So much of human culture is built around the contrast between light and dark, between the sun and the stars, between the known world of daytime and the mysterious infinite canvas of night. On a planet inside IC1101, that canvas would be permanently lit. You wouldn't invent the same myths. You wouldn't tell the same stories. The entire trajectory of your civilization's relationship with the sky would be different. Astronomy, if it developed at all, would be profoundly altered. Observing distant galaxies would be far more difficult through the ambient glow, and the very idea that you lived inside a galaxy, a concept that took humanity millennia to figure out, might be even harder to arrive at when the galaxy's light is everywhere and inescapable. A mainstream historical fact that resonates here. The philosopher Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers, asks why the night sky is dark if the universe contains infinitely many stars. If stars are spread uniformly in every direction, then every line of sight should eventually terminate on the surface of a star, and the sky should be blazing bright in every direction, day and night. Olbers posed this question formally in 1823, though others had raised similar puzzles earlier. The resolution involves a combination of factors, including the finite age of the universe, the finite speed of light, and the red shifting of distant light due to cosmic expansion. But on a planet deep inside IC1101, you would experience something closer to Olbers' nightmare. Not the full blazing brightness he imagined, because the stars aren't infinitely dense, but a persistent, inescapable glow that would make the paradox feel less like a thought experiment and more like a weather report. Scholars still argue about whether habitable planets could actually exist inside giant elliptical galaxies. The conditions are different from what we find in the Milky Way's spiral arms, but not necessarily hostile. Elliptical galaxies are relatively quiet places, with low rates of supernova explosions and minimal turbulence from spiral density waves. A planet orbiting a stable, long-lived star in such an environment might actually be quite peaceful, shielded from many of the disruptive events that can sterilize worlds in more active galaxies. On the other hand, the higher stellar density in the inner regions could increase the frequency of close stellar encounters where a passing star gravitationally disturbs a planetary system and sends planets flying off into interstellar space. The likelihood of this happening depends on exactly where in the galaxy you are and how tightly packed the stars are, and different research groups have reached different conclusions about the overall habitability of elliptical galaxies. The answer, as usual, is complicated. A quirky thought that cosmologists sometimes entertain. If intelligent life did arise on a planet deep inside IC1101, those beings would have a very different view of cosmology than we do. Their galaxy would be so vast that they might struggle to conceive of it as a single object. They might instead think of themselves as living in a boundless sea of stars with no edge and no structure, a kind of stellar fog extending in all directions. The idea that this fog is a discrete galaxy, one among billions, floating in a much larger universe of mostly empty space, would be profoundly counterintuitive. They'd be like fish born in the deep ocean, unable to imagine the concept of a shore. Their cosmology would start from fundamentally different assumptions, and their sense of scale, already warped by the sheer density of their stellar environment, might develop in ways we can barely imagine. There's also the question of what the other galaxies in the Able 2029 cluster would look like from inside IC 1101. From a planet near the centre, the surrounding cluster galaxies would be extremely difficult to detect, buried behind the foreground glow of IC 1101's own stars. But from a planet in the outskirts, near the galaxy's diffuse edge, you might see neighbouring galaxies as faint smudges in the ambient glow, ghostly shapes drifting slowly closer over millions of years before being absorbed by the gravitational embrace of the giant. You would be watching your galaxy's next meal approach. That would be an eerie thing to know, wouldn't it? To look up and see a galaxy falling toward you, knowing that in a few billion years it would merge with your own and add its stars to the already overwhelming sky. You'd be living inside a predator, watching it hunt. You let that thought linger as you drift back outward, away from your imaginary planet, away from the perpetual golden twilight of a C1101's interior. The galaxy recedes behind you, enormous and warm and ancient, and you carry with you the unsettling understanding that the biggest galaxy you've seen so far might not be the biggest one there is, because there's something else out there, something that doesn't announce itself with visible starlight at all, something that screams in a wavelength your eyes were never built to detect. The universe is noisy in ways you can't hear. Your eyes are tuned to a narrow sliver of the electromagnetic spectrum, the part we call visible light, and everything you've seen so far tonight, every star, every galaxy, every golden glow, has been painted in that sliver. But the electromagnetic spectrum is vast, stretching from gamma rays at one end, with wavelengths smaller than an atom, to radio waves at the other, with wavelengths longer than a football field. And when you tune your instruments to those longer wavelengths, to the radio end of the spectrum, the universe looks completely different. Galaxies that appear modest and unremarkable in visible light can suddenly reveal enormous structures extending millions of light years into space. Structures that are invisible to optical telescopes. Structures that dwarf the stellar bodies of even the largest galaxies. You're about to enter the domain of radio galaxies, and things are about to get significantly more unsettling. A radio galaxy is, at its core, a galaxy with an active supermassive black hole that is launching jets of plasma into intergalactic space at velocities approaching the speed of light. These jets are produced by the extreme physics near the black hole's event horizon, wherein falling matter spirals into an accretion disk, heats to billions of degrees, and generates magnetic fields so intense that they funnel some of the material outward in two narrow, oppositely directed beams. These beams punch through the galaxy like needles through fabric and keep going, ploughing into the intergalactic medium for millions of light years before finally slowing down and spreading out into vast, billowing clouds called lobes. The lobes glow in radio wavelengths because the electrons inside them are spiraling around magnetic field lines at relativistic speeds, emitting what's called synchrotron radiation. You can't see any of this with your eyes, but a radio telescope picks it up beautifully, and what it reveals is often breathtaking. The scale of these radio structures is difficult to communicate without sounding like you're exaggerating. The stellar body of a radio galaxy might be a few 100,000 light-years across, comparable to a large elliptical galaxy. Nothing too extraordinary. But the radio lobes can extend millions of light-years on either side, creating a total structure that is many times larger than the galaxy itself. It's as if your body were the size of a person, but your shadow stretched across an entire city. The galaxy is the seed. The lobes are the fruit, and the fruit can grow to dimensions that make IC1101 look, if not small, then at least not uniquely enormous. A mainstream historical fact that anchors this: radio astronomy essentially began by accident in 1932, when Carl Jansky, a physicist working for Bell Telephone Laboratories in New Jersey, was investigating sources of static that interfered with transatlantic radio communications. He built a large rotating antenna, which his colleagues nicknamed Jansky's merry-go-round, and used it to identify three types of static: nearby thunderstorms, distant thunderstorms, and a mysterious, persistent hiss that seemed to come from the centre of the Milky Way. Jansky had inadvertently discovered that the universe emits radio waves, and he did it while trying to solve a telephone problem. The discovery didn't make much of a splash at the time. Bell Labs wasn't particularly interested in cosmic radio signals, and Jansky was reassigned to other projects. But an amateur radio operator named Grote Reber read Jansky's papers, built a parabolic radio dish in his backyard in Wheaton, Illinois, and spent the next several years mapping the radio sky single-handedly. Reber's backyard dish, completed in 1937, was the world's first purpose-built radio telescope. The field that would eventually reveal the largest structures in the universe was born in a phone company's lab and raised in a suburban backyard. You have to admire the modesty of those origins. The physics of how jets are launched is still not fully understood, which is remarkable given that we've been studying them for decades. Scholars still argue about the exact mechanism that collimates the jets, meaning the process that keeps them narrow and focused over such enormous distances. The leading models involve a combination of magnetic fields threading the accretion disk and the rotational energy of the black hole itself, in a framework called the Blandford-Znajek mechanism, proposed in 1977. The spinning black hole twists the surrounding magnetic field lines into a tight helical configuration that acts like a nozzle, channeling energy and particles outward along the black hole's rotational axis. It's an elegant theory, and simulations support it reasonably well, but the details remain contentious. How exactly do the magnetic fields maintain their structure over millions of light years? How do the jets remain stable against the instabilities that should tear them apart? Why do some supermassive black holes produce powerful jets, while others, equally massive, produce none at all? These are open questions, each one capable of sustaining an entire career's worth of research. A quirky detail about radio galaxies that delights astronomers and confuses everyone else. The lobes of a radio galaxy are among the most voluminous structures in the universe, but they contain almost no matter. The plasma inside a lobe is extraordinarily diffuse, often less dense than the best vacuum achievable in any laboratory on Earth. What fills the lobes is energy, stored in magnetic fields and relativistic electrons, spread across a volume that can exceed millions of cubic light years. If you could somehow scoop up all the matter in a radio lobe the size of the Milky Way, you might end up with less material than a single asteroid. The lobes are essentially enormous, luminous bubbles of almost nothing. Ghosts on a cosmic scale, visible only in radio light, magnificent and empty. You sit with that image for a moment. Enormous bubbles of magnetized nothing, glowing in wavelengths you can't see, stretching across distances that would take millions of years to cross at the speed of light. And somewhere out there, one of these radio structures grew so impossibly large that when astronomers finally measured its full extent, they realized they were looking at the single biggest thing associated with any galaxy ever found. Not the biggest galaxy by starlight, the biggest structure connected to a galaxy by any measure, and unlike IC1101, which has been known for decades, this one was hiding in plain sight until very recently. Its name is Alcionius, and when you first hear it, you might think it sounds like a pharmaceutical product, or maybe a character from a fantasy novel that takes itself too seriously. But the name comes from Greek mythology. Alcionius was one of the giants, the enormous sons of Gaia who waged war against the Olympian gods in a conflict called the Gigantomachy. According to the myth, Alcionius was immortal as long as he remained in his homeland of Pallene, and Heracles had to drag him beyond its borders before he could be killed. It's a fitting name for a galaxy that seems to draw its power from the very space it occupies, a structure so tied to its environment that understanding one requires understanding the other. The astronomers who named it clearly had a sense of occasion, and honestly, when you see the numbers, you'll agree they earned the right to be dramatic. Alcionius is a giant radio galaxy located approximately 3 billion light-years from Earth. Its host galaxy, the visible collection of stars at its centre, is not particularly extraordinary. It's a fairly standard elliptical galaxy, maybe a couple of 100,000 light-years across, sitting in a region of space that doesn't stand out as especially dense or unusual. By stellar metrics alone, Alcionius would be unremarkable, a background character in the cosmic census. But when you observe it in radio wavelengths, the picture changes completely. Extending outward from the host galaxy in two opposite directions are radio lobes of almost incomprehensible size. The total extent of these lobes, measured from tip to tip, is approximately 16 million light-years. 16 million? That's roughly 160 times the diameter of the Milky Way. It's nearly 3 times the most generous size estimates for IC 1101. If you could somehow see Alcionius in its entirety with your naked eyes, it would span an area of the sky larger than the full moon, despite being 3 billion light-years away. The only reason you can't see it is that it radiates almost exclusively in wavelengths your retinas were never designed to detect. The discovery of Alcionius was announced in a paper published in early 2022 by a team led by Martijn Owe, a doctoral researcher at Leiden Observatory in the Netherlands. The paper landed in the astronomical community like a stone dropped into a still pond. Giant radio galaxies were already known. There are hundreds of them catalogued, some with lobes extending 1 million light-years or more. But nothing this large had ever been measured. The previous record holders, galaxies like Hercules A and 3C236, had lobes extending a few million light-years at most. Alcionius shattered the record by a substantial margin, and it did so with a host galaxy that, by every conventional measure, had no business producing something this enormous. A mainstream historical fact that puts this in context: the first giant radio galaxies were identified in the 1950s and 60s, during the early golden age of radio astronomy. Cygnus A, discovered in 1953, was among the first radio sources to be identified with a distant galaxy, and its twin lobes became the archetype for how astronomers understood radio galaxies for decades. Cygnus A's lobes stretch about 500,000 light-years from end to end, which seemed impossibly large at the time. The idea that something could be 160 times wider than the Milky Way and connected to a single galaxy would have seemed absurd to the astronomers of that era. But the universe has a long history of making absurdity into routine, and each generation of telescopes has revealed structures larger than the last generation thought possible. The discovery paper for Alcionius was carefully measured in its claims, as good science tends to be, but the underlying message was unmistakable. The universe can build structures far larger than anyone had expected, and the mechanisms that produce them are not yet well understood. The team measured the lobes using data from the Low Frequency Array, or LOFAR, a vast network of radio antennas spread across northern Europe. LOFAR operates at low radio frequencies, which are particularly well suited for detecting the diffuse, aged emission from old radio lobes, the kind of emission that higher frequency radio telescopes tend to miss. The key insight was that Alcionius's lobes were there in the data all along, but previous processing techniques had filtered them out as noise. They were hiding in the static, like a whisper buried in a crowd, waiting for someone with the right tools and the right patience to pull them out. Scholars still argue about how to interpret the size of Alcionius in the context of existing theoretical models. Most models of radio galaxy evolution predict that lobes should eventually slow down and stall as they push against the resistance of the intergalactic medium, the thin plasma that fills the space between galaxies. The denser the medium, the harder it is for the lobes to expand, and the smaller the final structure should be. For Alcionius to have grown so large, either the intergalactic medium in its vicinity is unusually sparse, allowing the lobes to expand with minimal resistance, or the jets that inflated the lobes were active for an extraordinarily long time, or both. Untangling these possibilities requires detailed observations of the environment around Alcionius, and that work is still ongoing. A quirky detail about the naming process. The team considered several names before settling on Alcionius. In academic astronomy, there's no formal requirement to name radio galaxies anything evocative. Most are simply referred to by their catalogue designations, strings of numbers and letters that tell you the survey they came from and their coordinates on the sky. Alcionius's official designation is a forgettable jumble of letters and digits that nobody outside the field would remember for 5 seconds. But the team chose to give it a proper name, a mythological name, because they recognised that what they had found deserved to be remembered as more than a coordinate. It's a small act of poetry in a field that doesn't always make room for it, and it stuck. When people talk about the biggest galaxy ever discovered, they say Alcionius, and the giant of Greek mythology lives again in the radio glow of intergalactic plasma, 16 million light-years wide. You hold that number in your mind, 16 million light-years, and you try not to let it flatten into just another big number. You try to feel it. 16 million years of travel for the fastest thing in the universe. And this was hiding in data that had already been collected, just waiting to be seen. The story of how Alcionius was found is, in many ways, more remarkable than the object itself. Because Alcionius wasn't lurking at the edge of the observable universe, hiding behind some curtain of cosmic dust in a region no telescope had ever surveyed. It was right there, sitting in data that had been publicly available for years, captured by a telescope network that hundreds of astronomers had already used for other projects. The largest structure ever associated with a galaxy was not discovered by building a bigger telescope, or launching a new satellite, or spending billions of dollars on cutting-edge hardware. It was discovered by looking at old data more carefully. There's something almost embarrassing about that, and something deeply inspiring. LOFAR, the telescope array responsible for capturing the data, is not a single dish pointed at the sky. It's a collection of roughly 20,000 individual radio antennas spread across the Netherlands and into several other European countries including Germany, France, Sweden, Poland, and the United Kingdom. Each antenna looks nothing like what you'd picture when you imagine a radio telescope. There are no giant white dishes, no dramatic parabolic reflectors. LOFAR's antennas are small, flat, unassuming panels arranged in clusters in open fields, sometimes nestled between farms and bicycle paths. They look more like solar panels having an identity crisis than instruments capable of peering billions of light-years into space. But their power comes from their numbers and their coordination. By combining the signals from thousands of antennas spread across a continent, LOFAR can achieve angular resolution comparable to a single dish hundreds of kilometers wide. It sees the radio sky with extraordinary sharpness, and it does so at low frequencies between 10 and 240 MHz, a range that is particularly sensitive to the old, faint, diffuse emission that characterizes the lobes of giant radio galaxies. The LOFAR 2-meter sky survey, or LOTSS, has been systematically mapping the northern radio sky since 2017, producing images of unprecedented sensitivity and resolution at low frequencies. By the time Martinier and his colleagues began their search for giant radio galaxies, LOTSS had already covered a significant fraction of the sky and generated enormous data sets. The data was there. The photons had been collected. The hard part was processing it in a way that didn't accidentally throw away the very signals they were looking for. And this is where the detective story gets interesting. Standard radio image processing involves several steps that can inadvertently suppress large-scale, diffuse emission. When you're building a radio image from interferometric data, you're essentially combining signals from many pairs of antennas to reconstruct a picture of the sky. The shortest baselines, the pairs of antennas that are closest together, are sensitive to large-scale structures. The longest baselines, the most widely separated pairs, are sensitive to fine details. Most processing pipelines are optimized for point sources and compact structures, the things astronomers most commonly study, and they tend to filter out the smooth, extended emission that giant radio lobes produce. It's like a camera with an autofocus system that's brilliant at capturing faces but systematically blurs out the landscape behind them. The landscape is there, but the technology is inadvertently ignoring it. A mainstream historical fact that parallels this nicely: the cosmic microwave background radiation, the afterglow of the Big Bang, was discovered in 1964 by Arno Penzias and Robert Wilson at Bell Labs, the same institution where Carl Jansky had detected cosmic radio emission 3 decades earlier. Penzias and Wilson were calibrating a radio antenna for satellite communications and kept finding a persistent, unexplained hiss that they couldn't eliminate. They checked for every possible source of interference, including pigeon droppings on the antenna, which they carefully cleaned off. The hiss remained. It turned out to be the remnant radiation from the birth of the universe itself. Like Alcionius, it was hiding in plain sight, masquerading as noise. The history of radio astronomy is, in a very real sense, a history of learning to hear signals that were always there but that everyone assumed were static. Hui and his team developed a new processing approach that was specifically designed to preserve large-scale emission. They reprocessed the LOTSS data with careful attention to the short baselines, ensuring that the diffuse structures weren't being filtered away. They also used a technique involving image subtraction, where compact sources are modelled and removed from the data first, leaving behind only the extended emission. It's a painstaking process, requiring careful calibration and a deep understanding of the telescope's response to different spatial scales. And when they applied this technique to a systematic survey of the radio sky, Alcionius emerged from the noise like a developing photograph. 2 enormous lobes, previously invisible in standard processing, materialized on either side of an unremarkable elliptical galaxy, stretching across a span of sky that corresponded to 16 million light-years at the galaxy's distance. Scholars still argue about whether the processing techniques used to reveal Alcionius might have introduced artifacts, spurious features that aren't real, but are instead byproducts of the data reduction process. This is a standard concern in radio astronomy, where processing choices can significantly affect the final image. The team addressed this by using multiple independent processing methods and checking for consistency, and the consensus in the field is that Alcionius's lobes are genuine. But the debate highlights a broader truth about observational science. What you see depends not just on what's out there, but on how you choose to look. Every telescope, every processing pipeline, every analytical choice is a filter, and every filter lets some things through while blocking others. The universe is full of things we haven't seen yet, not because they're hiding, but because we haven't built the right filter. A quirky footnote about the discovery: Way was a graduate student when the Alcionius paper was published, which means one of the most significant discoveries in extragalactic astronomy in recent years was made by someone who hadn't even finished their doctoral thesis yet. This isn't as unusual as it might sound. Graduate students and postdoctoral researchers do the bulk of hands-on astronomical research, spending long hours processing data, writing code, checking results, and occasionally stumbling onto something that changes how we understand the universe. The hierarchy of academia often means that the most groundbreaking work is done by the people with the least job security, which is a structural irony the field has been grappling with for generations. You think about that for a moment. About the patience required to sift through terabytes of radio data looking for something no one was sure existed. about the intellectual courage to question whether standard processing was accidentally erasing the universe's largest structures, and about the quiet thrill of watching those lobes appear on a screen, faint and vast and undeniably real, a giant waking up in the data. Here is the part that keeps astrophysicists awake at night, and not in the cozy, sleepy podcast way that you're experiencing right now. The host galaxy of Alcionius is, by every conventional measure, ordinary. It's not the most massive galaxy in its neighbourhood. Its supermassive black hole, while certainly large, is not unusually so. Its stellar mass is estimated at roughly 240 billion solar masses, which sounds impressive until you remember that the Milky Way has a stellar mass of about 50 to 60 billion solar masses. Alcionius's host is maybe 4 or 5 times the mass of your galaxy. That's big, sure, but it's nowhere near the most massive elliptical galaxies known. Galaxies 10 or 20 times more massive exist, and plenty of them have radio jets that are far less spectacular. The galaxy at the centre of Alcionius is, to borrow an earlier metaphor, a mid-range sedan that somehow produced the largest sonic boom in the history of the atmosphere. It shouldn't work, but it did. This is what makes Alcionius scientifically fascinating rather than just impressively large. If the biggest radio structure in the universe were anchored by the biggest, most active, most powerful galaxy in the universe, the explanation would be straightforward. Big engine, big exhaust, simple. But Alcionius doesn't follow that script. Its engine is modest. Its exhaust is cosmic. And the gap between those two facts is where the interesting physics lives. One hypothesis is that the intergalactic environment around Alcionius is unusually sparse. If the space surrounding a radio galaxy contains very little matter, the jets encounter minimal resistance and can expand much farther before dissipating. Think of it like blowing smoke in a windy room versus blowing smoke in a perfectly still one. In the still room, the smoke drifts outward and maintains its structure for much longer. The intergalactic medium is not uniform. Some regions are denser than others, threaded with filaments of warm-hot gas that connect galaxy clusters like roads between cities. Other regions are relative voids, under-dense patches where the gas is thin and feeble. If Alcionius happens to sit in one of these cosmic backwaters, its jets might have had an unusually easy path outward, inflating their lobes to extraordinary dimensions simply because nothing was in the way. A mainstream historical fact that supports this line of thinking: the large-scale distribution of matter in the universe was first mapped in detail by the Harvard-Smithsonian Center for Astrophysics redshift surveys in the 1980s. These surveys, led by astronomers including Margaret Geller and John Hucherer, revealed that galaxies are not distributed randomly through space, but are organized into enormous structures, walls and filaments and voids that look like the foam in a bubble bath when viewed at the larger scales. The voids in particular are staggeringly empty, some spanning hundreds of millions of light years with almost no galaxies inside them. The discovery of this cosmic web fundamentally changed how astronomers thought about the universe's architecture, and it's precisely this architecture, the distribution of dense and sparse regions, that might explain why some radio galaxies can grow lobes 16 million light-years wide, while others fizzle out after a few 100,000. Another hypothesis focuses on the age of the jets. Radio lobes don't inflate instantaneously. They grow over tens or hundreds of millions of years as the jets continuously pump energy into them. Most radio galaxies go through cycles of activity, with the jets switching on and off as the supermassive black hole's fuel supply fluctuates. A typical active phase might last 10 to 100 million years, after which the jets shut down and the lobes begin to fade. If Alcionius's jets were active for an unusually long period, or if they underwent multiple cycles of activity with relatively short quiet intervals, the cumulative effect could produce lobes far larger than a single episode of activity would allow. The lobes we see today might be the accumulated output of billions of years of intermittent jet activity, layered on top of each other like coats of paint, each cycle pushing the boundaries a little farther out. Scholars still argue about which factor dominates. Some researchers favour the environmental explanation, pointing to preliminary evidence that the gas density around Alcionius is indeed lower than average. Others emphasise the duty cycle of the jets, arguing that the total energy output matters more than the resistance of the medium. A third camp suggests that both factors are important, and that Alcionius represents a rare coincidence. A galaxy with a sufficiently persistent jet in a sufficiently empty environment, a cosmic sweet spot that produces an outsized structure through a combination of favourable circumstances rather than any single exceptional property. The debate is young and vigorous, with new observations and simulations appearing regularly, and it may take years to settle. A quirky detail that adds another layer of mystery. The radio lobes of Alcionius are remarkably symmetrical. Both lobes extend roughly the same distance from the host galaxy, and their overall morphology is fairly balanced. This is not guaranteed. Many radio galaxies have asymmetric lobes, with one side significantly larger or brighter than the other, usually because the intergalactic medium is denser on one side, creating more resistance and slowing the jet's advance. The symmetry of Alcionius's lobes suggests that the surrounding environment is relatively uniform in all directions, which is consistent with the idea that the galaxy sits in an underdense region where the gas is evenly thin. It's as if the universe cleared a space for Alcionius, swept the room clean in every direction, and said, "Go ahead, stretch out, see how far you can reach." You lie there thinking about how strange it is that the biggest thing ever connected to a galaxy was produced by something so unremarkable. It feels counterintuitive, almost unfair, like finding out that the tallest tree in the forest grew from the most ordinary seed. But the universe has never been particularly concerned with fairness, or with matching cause to effect in ways that satisfy human intuition. Sometimes the extraordinary emerges from the mundane, not through exceptional force but through exceptional circumstance, through the quiet alignment of conditions that no one was watching for because no one expected them to matter. Between the galaxies, there is something. This surprises most people. The popular image of intergalactic space is pure emptiness, a perfect vacuum stretching endlessly between the bright islands of stars, and it's true that intergalactic space is extraordinarily empty by any human standard. If you could teleport to a random point between galaxies, you'd find yourself in a region so devoid of matter that there might be only 1 or 2 atoms per cubic meter. For comparison, the air you're breathing right now contains roughly 25 quintillion molecules per cubic centimeter. Intergalactic space is empty in a way that makes the emptiest laboratory vacuum look like a packed subway car. And yet, collectively, this thinly scattered matter adds up to something significant. In fact, the diffuse gas between galaxies contains more total mass than all the stars in all the galaxies combined. The ocean between the islands is heavier than the islands themselves. It's one of the great counterintuitive truths of cosmology, and it's directly relevant to understanding how something like Alcionius grows to the size it does. This intergalactic gas is called the intergalactic medium, or IgM, and it's mostly hydrogen and helium, the primordial elements forged in the first few minutes after the Big Bang. Some of it has been enriched with heavier elements blown out of galaxies by supernova winds and active galactic nuclei. But the bulk of it is pristine stuff, barely touched since the universe began. Its temperature varies enormously depending on where you are. In the vast cosmic voids, far from any galaxy cluster, the gas is relatively cool, a few thousand degrees and nearly invisible. But in and around galaxy clusters, the gas has been shock heated to temperatures of tens or even hundreds of millions of degrees, forming a searing plasma that glows brightly in X-rays. This hot component is called the warm-hot intergalactic medium, or WIM, and finding it has been one of the great observational challenges of modern astrophysics. A mainstream historical fact that connects here. The existence of the intergalactic medium was first inferred in the 1960s through a clever technique called the Gunn-Peterson test. Astronomers James Gunn and Bruce Peterson predicted that if neutral hydrogen gas existed between galaxies, it would absorb specific wavelengths of light from distant quasars, creating a characteristic absorption trough in the quasar's spectrum. When astronomers looked at actual quasar spectra, they found not a single smooth trough, but a dense forest of individual absorption lines, each one corresponding to a separate cloud of hydrogen gas at a different distance along the line of sight. This Lyman Alpha forest, as it became known, provided the first direct evidence that the space between galaxies is not truly empty, but is instead filled with a filamentary web of gas stretching across the observable universe. Every quasar spectrum is a core sample drilled through billions of light-years of intergalactic real estate, and the absorption lines are the geological layers you encounter along the way. The reason this matters for Alcionius is that the intergalactic medium is the material through which its radio lobes are expanding. When the relativistic jets from Alcionius's central black hole slam into this ambient gas, they create shock waves at the leading edges of the lobes, compressing and heating the intergalactic medium like a snowplow pushing through fresh powder. The lobes inflate behind these shock waves, filling with magnetized plasma and relativistic electrons, growing larger and larger as the jets continue to pump energy outward. The rate at which the lobes can expand depends critically on the density of the medium they're pushing through. Dense medium means more resistance, slower expansion, smaller lobes. Sparse medium means less resistance, faster expansion, and potentially the kind of monstrous proportions you see in Alcionius. This is why the local environment of Alcionius matters so much. If you could map the density of the intergalactic medium in the region surrounding Alcionius with perfect precision, you'd have a much better understanding of why its lobes grew so large. Preliminary analyses suggest that Alcionius does indeed reside in a region of below-average density, consistent with the environmental explanation for its extraordinary size. But below average is not zero. There is still gas out there, still resistance, still friction. The lobes are not expanding into nothing. They're expanding into something incredibly thin but measurably present, and the interaction between the lobes and this tenuous medium shapes the structure you observe. Scholars still argue about how much energy is transferred from the radio lobes to the intergalactic medium during this expansion. This process, called AGN feedback, is thought to play a crucial role in regulating the formation of stars and the growth of galaxies across the universe. When radio lobes inflate into the intergalactic medium, they heat the gas and prevent it from cooling and collapsing into new galaxies. In galaxy clusters, this feedback mechanism is believed to solve a long-standing puzzle. Why do galaxy clusters contain far fewer galaxies than simple models predict? The answer, or at least a significant part of it, is that the radio jets from the central galaxy keep the surrounding gas too hot to form stars. Alcionius, with its 16 million light-year lobes, is performing this feedback on an almost unimaginable scale, heating and stirring the intergalactic medium across a volume that dwarfs most galaxy clusters. A quirky detail that illustrates just how pervasive this process is. Some of the largest cavities ever observed in the X-ray emitting gas of galaxy clusters were carved by radio jets. These cavities appear as dark bubbles in X-ray images, regions where the hot gas has been displaced by the expanding radio lobes. The cavities in the Perseus cluster, for instance, are each about 200,000 light-years wide, roughly the size of the Milky Way. They were inflated by jets from the central galaxy, NGC 1275, and they contain enough energy to power the Milky Way's entire stellar output for 100 million years. Now, imagine the cavities that Alcionius must be carving. At 16 million light-years across, its lobes are displacing a volume of intergalactic gas so vast that the energy involved is difficult to calculate with any precision. The universe's largest galaxy, by radio extent, is also one of its most powerful environmental engineers, reshaping the cosmos around it with the quiet persistence of a river carving a canyon. You let that image carry you forward, the slow inflation of lobes pushing through invisible gas, carving cavities in the hot plasma between galaxies, shaping the architecture of the universe one shockwave at a time. You've been zooming in and out all night, moving from the scale of individual stars to the scale of galaxies to the scale of radio lobes millions of light years wide. Now you pull back one more time, farther than before, until the galaxies themselves become specks, and the thing you're looking at is the universe's largest architecture. The cosmic web, the scaffolding on which everything hangs, and once you see it, once you really take in its structure, you'll understand why some galaxies grow to absurd sizes while others remain modest, why location matters as much as appetite, and why the universe is less like a scattering of random objects and more like a living, breathing network with highways and intersections and vast haunted deserts in between. The cosmic web is the large-scale structure of the universe, and it looks exactly like its name suggests. Imagine a three-dimensional spiderweb made of light, except the strands are hundreds of millions of light-years long, and the spaces between them are voids so empty that they make intergalactic space seem crowded. The strands are called filaments, and they're made of dark matter, gas, and galaxies, all threaded together by gravity into long, thin structures that connect the densest regions of the universe. Where filaments intersect, you find nodes, massive clumps of matter where galaxy clusters form. Where filaments are absent, you find voids, enormous empty bubbles that can span 300 million light-years or more with almost nothing inside them. The whole thing looks like the structure of a sponge, or the network of neurons in a brain, or the pattern of soap bubbles in a sink, depending on which metaphor appeals to you most. All of them work. None of them are quite adequate. A mainstream historical fact that grounds this. The first comprehensive maps of the cosmic web were produced in the late 1980s and 1990s by galaxy redshift surveys, most notably the CFA surveys led by Margaret Geller and John Huckra, which you encountered briefly a few sections ago. Their famous Stickman map, published in 1989, showed for the first time that galaxies are distributed in thin sheets and filaments surrounding enormous voids. The image was shocking. Until that point, most cosmologists had assumed the universe was roughly homogeneous at large scales, with galaxies sprinkled more or less uniformly through space. The discovery that the universe is instead organized into this intricate web-like pattern was a paradigm shift, and it sparked decades of theoretical and computational work aimed at understanding how this structure formed and evolved. The answer, broadly speaking, is gravity plus time. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, but not quite. There were tiny density fluctuations, quantum hiccups left over from the inflationary epoch, regions where the density was slightly higher or slightly lower than average. Over billions of years, gravity amplified these fluctuations. Slightly denser regions attracted more matter from their surroundings, growing denser still, while slightly underdense regions lost matter and became emptier. The dense regions collapsed along their shortest axes first, forming flat sheets called walls or pancakes, then along their next shortest axes, forming filaments, and finally along all three axes simultaneously, forming compact, roughly spherical nodes where galaxy clusters reside. This process of hierarchical gravitational collapse is beautifully reproduced by cosmological simulations, which can start from the observed fluctuations in the cosmic microwave background and evolve them forward in time to produce a cosmic web that matches the one we actually observe. It's one of the great triumphs of modern cosmology, a story that connects quantum physics in the first fraction of a second to the largest structures visible 13 billion years later. Now here is why this matters for the biggest galaxies. The nodes of the cosmic web, the places where multiple filaments converge, are the densest environments in the universe. Galaxy clusters form at these nodes, and the biggest galaxies within those clusters, the brightest cluster galaxies like IC 1101, sit at the very centre of the node, at the bottom of the deepest gravitational well. They grow large because everything flows toward them. Galaxies slide along the filaments, drawn by gravity toward the nodes, and when they arrive, they are consumed by the central giant. The cosmic web is essentially a feeding network, a system of gravitational highways that channel raw material toward the most massive objects at the intersections. IC1101 grew enormous because it sits at one of these intersections, patiently absorbing everything the filaments deliver. Alcionius, interestingly, does not sit at a major node. This is one of the most intriguing aspects of its discovery. Its host galaxy appears to reside in a relatively unremarkable part of the cosmic web, not at the centre of a massive cluster, but in a more peripheral location where the ambient density is lower. This is consistent with the environmental hypothesis for its enormous radio lobes. Away from the dense nodes, the intergalactic medium is thinner, offering less resistance to the expanding jets. The cosmic web, in a sense, gave Alcionius room to stretch. It's like the difference between inflating a balloon inside a crowded elevator versus inflating one in an open field. The balloon is the same. The space available is not. Scholars still argue about the precise relationship between a galaxy's position in the cosmic web and its radio properties. Some studies suggest that giant radio galaxies are preferentially found in low-density environments, which would support the idea that sparse surroundings are a necessary condition for extreme lobe growth. Other studies find no strong environmental dependence, suggesting that internal factors like jet power and duty cycle matter more. The tension between these findings is not yet resolved, and it's possible that different mechanisms dominate in different cases. A quirky detail about the cosmic web that tickles cosmologists: the network of filaments connecting galaxy clusters bears a striking resemblance to the network of neurons connecting regions of the brain. This is not a coincidence in any mystical sense, but rather a consequence of similar mathematical processes. Both networks are shaped by the physics of diffusion and connectivity in complex systems. Some researchers have even published papers quantitatively comparing the two structures, showing that the number of connections per node, the distribution of filament lengths, and the overall topology are surprisingly similar. The universe, at its largest scales, is organized like a thought. Make of that what you will as you drift closer to sleep. Alcionius holds the crown, but it doesn't hold it alone in a vacuum. The universe has produced a startling number of oversized radio galaxies, and spending some time with the runners-up gives you a better sense of just how extreme the upper end of the galactic size distribution really is. These are the galaxies that would have been record holders in any other era, the ones that made astronomers recalibrate their instruments and question their assumptions, only to be quietly eclipsed when something even bigger turned up. They deserve their moment in the warm glow of your half-closed attention. Start with Hercules A, also known as 3C348. This is a radio galaxy located about 2 billion light-years from Earth, and it's one of the most visually dramatic objects in the radio sky. Its host galaxy is a massive elliptical, significantly more luminous and heavier than Alcionius' host, sitting at the centre of a galaxy cluster. The jets emerging from its central black hole are spectacular, producing lobes that extend roughly 1.5 million light-years from end to end. In combined radio and optical images, the lobes appear as enormous purple clouds flanking the golden elliptical, like wings on some ancient celestial bird. What makes Hercules A especially interesting is the structure within its lobes. They're not smooth. They contain rings and knots and filaments of enhanced emission that suggest the jets have undergone multiple episodes of activity, each burst inflating a new layer within the existing lobes. It's like tree rings in a cosmic trunk, each ring recording a period when the black hole woke up and blasted energy outward before settling back to sleep. Then there's 3C236, which for a long time was considered the largest known structure in the universe. This giant radio galaxy lies about 490 million light-years from Earth, which is relatively nearby by cosmological standards, and its lobes stretch approximately 15 million light-years from end to end. That's almost as large as Alcionius, and for decades it held the record with comfortable authority. The host galaxy is a modest elliptical, not particularly remarkable, which foreshadowed the same puzzle that Alcionius would later present in even starker terms. A mainstream historical fact worth noting: 3C236 was first identified as an unusually large radio source in the 1970s, during a period when radio astronomers were systematically cataloguing the brightest sources in the sky. Its full extent wasn't appreciated until later surveys with more sensitive instruments revealed just how far its lobes extended. The measurement history of 3C236 mirrors the broader history of giant radio galaxies, a story of gradually improving technology, revealing gradually larger structures, each one pushing the boundary of what seemed physically possible. Another contender worth visiting is Phoenix A, the central galaxy of the Phoenix cluster, one of the most extreme galaxy clusters ever discovered. Phoenix A is remarkable not primarily for its radio extent, but for its sheer mass and its astonishing rate of star formation. Most brightest cluster galaxies have essentially stopped forming new stars, their gas supplies exhausted or kept too hot by AGN feedback to collapse. But Phoenix A is producing new stars at a rate of roughly 500 to 800 solar masses per year, which is hundreds of times the star formation rate of the Milky Way. This furious activity appears to be fueled by a cooling flow, a stream of hot cluster gas that has managed to cool and condense despite the heating efforts of the central black hole. Scholars still argue about why the feedback mechanism that suppresses star formation in almost every other brightest cluster galaxy has apparently failed in Phoenix A. Some suggest that the current episode of AGN activity is too young or too weak to counteract the cooling flow. Others propose that the cooling is happening asymmetrically, in directions not covered by the jets. The Phoenix cluster is, in essence, a case study in what happens when the cosmic thermostat breaks. A quirky entry in the roster of oversized galaxies is IC2101, not to be confused with the IC1101 you met earlier. IC2101 is a far less famous object, but its name has caused confusion in more than one undergraduate astronomy class, leading to at least a few awkward exam answers that mixed up the two. The universe, apparently, is not above recycling catalogue numbers in ways designed to trip up students. Then there is the broader category of giant radio galaxies, or GRGs, defined as radio galaxies whose total projected size exceeds roughly 2 million light-years. Before Alcionius's discovery, A few hundred GRGs were known, scattered across the sky in various environments. Some live in galaxy clusters, some live in relative isolation, some have powerful active jets, others have faded relic lobes that suggest the jet shut off long ago. The diversity among GRGs suggests that there is no single recipe for producing one. Size alone doesn't predict morphology, environment doesn't fully predict size, and jet power doesn't fully predict either. The population is messy and heterogeneous, which is exactly what you'd expect from a phenomenon governed by multiple interacting variables, none of which dominates in every case. What unites all these objects, from Hercules A to 3C236 to Phoenix A to the hundreds of catalogued GRGs, is that they represent the extreme tail of a distribution. For every galaxy with lobes stretching millions of light years, there are thousands with lobes a fraction of that size, and millions with no radio lobes at all. The biggest radio galaxies are outliers, statistical anomalies produced by rare combinations of jet power, environmental conditions, duty cycle, and cosmic timing. They are the tallest people in a city of billions, the oldest trees in a forest that stretches to the horizon. They're not typical of anything. They're interesting precisely because they're not typical. You let the parade of giants pass through your mind, each one slightly different, each one pushing the limits of what a galaxy can become when the conditions are right. And you find yourself wondering inevitably whether the parade is over, whether Alcionius really is the biggest, or whether something larger is out there, waiting in data not yet processed, hiding in wavelengths not yet surveyed, patient and colossal, and utterly indifferent to whether anyone ever finds it. The honest answer is that nobody knows. Nobody knows whether Alcionius is the largest galaxy-associated structure in the observable universe, or merely the largest one we've found so far. And if the history of astronomy teaches you anything, it's that records in this field tend to be temporary. Every generation of telescopes has revealed objects larger, more distant, more energetic, or more bizarre than anyone thought possible. The universe has a consistent track record of being bigger than our instruments can show us, and there's no reason to believe that pattern has suddenly stopped. Consider what we can't see yet. The observable universe has a radius of about 46 billion light-years, and it contains an estimated 2 trillion galaxies, a number that itself was revised dramatically upward in 2016, when a team led by Christopher Consolis at the University of Nottingham used deep survey data to estimate how many faint small galaxies had been missed by previous counts. 2 trillion galaxies, and we have detailed radio observations of only a small fraction of them. The LOFAR survey that revealed Alcionius has covered a significant portion of the northern sky, but it hasn't covered all of it, and it's limited to the radio frequencies and sensitivities achievable with current technology. There could be giant radio galaxies in the southern sky that no comparable survey has yet reached. There could be radio structures at frequencies below LOFAR's range that would require entirely different instruments to detect. There could be lobes so old and faint that even LOFAR's sensitivity isn't enough to pick them up. This is where the Square Kilometre Array enters the story. The SKA is a next-generation radio telescope currently under construction across 2 continents, with low-frequency antennas being built in Western Australia and mid-frequency dishes being installed in South Africa. When completed, it will be the most sensitive radio telescope ever built, capable of detecting signals so faint that current instruments would need thousands of years of observation time to match. The SKA's sensitivity and its coverage of the southern sky, which has been comparatively neglected by Northern Hemisphere facilities like LOFAR, make it the instrument most likely to discover the next Alcionius, if one exists. Its first science observations are expected within the next few years, and the radio astronomy community is buzzing with anticipation about what it might reveal. A mainstream historical fact that captures the ambition of the SKA The project has been in development since the 1990s, making it one of the longest gestating scientific instruments in history. Its name refers to the total collecting area of its antennas, which will approach 1 square kilometre when all phases are complete. That's roughly 50 times the collecting area of the next largest radio telescope array currently in operation. Building it has required unprecedented international cooperation, with contributions from over a dozen countries and engineering challenges that have pushed the boundaries of antenna design, data processing, and signal transmission. The data rates alone are staggering. When fully operational, the SKA will generate more data per day than the entire global internet traffic. Processing this torrent of information will require dedicated supercomputing facilities that are themselves among the most powerful in the world. The telescope designed to find the universe's largest structures will itself be one of the largest scientific instruments ever constructed. There's a poetic symmetry in that. Scholars still argue about what the theoretical maximum size of a radio galaxy might be. Some models suggest that there is a natural upper limit imposed by the age of the universe. A radio jet, no matter how powerful, can only propagate for as long as the universe has existed. At roughly 13.8 billion years old, the universe sets a hard cap on how far a jet can travel, even at nearly the speed of light. But jets don't travel through empty space. They push against the intergalactic medium, and this resistance slows them considerably. Realistic estimates of maximum lobe extent depend on assumptions about jet power, duty cycle, and environmental density, and they range from a few tens of millions of light years to perhaps 100 million light years in the most extreme theoretical scenarios. Alcionius, at 16 million light years, is well within the theoretical envelope, which means there's plenty of room for something bigger. There's also the question of what we mean by biggest galaxy. If you define size by stellar extent, IC 1101 is still among the champions, its diffuse envelope of stars stretching millions of light years. If you define size by radio extent, Alcionius wins decisively. But what about other wavelengths? What about the X-ray halos that surround some galaxy clusters, extending tens of millions of light years? What about the gravitational influence of a galaxy's dark matter halo, which can extend even farther? The answer to what is the biggest galaxy depends entirely on what you choose to measure, and as instruments improve, the definitions are likely to shift. A quirky thought that some theoretical astrophysicists entertain. In the far future, as the universe continues to expand and galaxies within gravitationally bound clusters merge together, the distinction between individual galaxies will eventually disappear entirely. Each galaxy cluster will consolidate into a single, enormous elliptical galaxy containing all the stars from all its former members. These future megagalaxies will be far larger than anything that currently exists, but they'll also be profoundly lonely, separated from each other by expanding voids so vast that light from one will never reach another. The biggest galaxy in the universe hasn't been built yet. It's being assembled right now, slowly, merger by merger, and it won't be finished for billions of years. But when it is, it will make Alcionius look like a preliminary sketch. You let that thought expand in your mind, the idea that the cosmic construction project is still underway, still adding bricks, still merging blueprints. Every galaxy you've encountered tonight, from the Milky Way to IC 1101 to Alcionius, is a snapshot of a work in progress. The universe isn't finished building, it's just letting you peek at the construction site while you drift towards sleep. The giants are not just spectacles, they're instruments. They tell us something about the deepest forces governing the fate of everything, forces that operate on scales so large and over timelines so long that individual galaxies, even colossal ones, are just data points in the argument. And the argument, the one that cosmologists have been having with increasing urgency since the late 1990s, is about what happens next. Not next year, not next century. Next, as in the ultimate trajectory of the universe, the final chapter of a story that began 13.8 billion years ago with a burst of energy so intense that it created space and time themselves. The biggest galaxies in the universe are characters in that story, and how they evolve, how they grow, how they eventually stop growing, tells us something about the ending. The key player in this cosmic drama is dark energy, the mysterious force that is causing the expansion of the universe to accelerate. Before 1998, most cosmologists assumed that the expansion of the universe was gradually slowing down, decelerating under the gravitational pull of all the matter it contained. This was the intuitive expectation. Throw a ball upward and gravity slows it down. The universe, having been thrown outward by the Big Bang, should similarly slow down over time. But in 1998, two independent teams studying distant Type Ia supernovae discovered that the expansion is not slowing down. It's speeding up. The ball is not falling back. It's accelerating away, faster and faster, driven by something that acts like anti-gravity on the largest scales. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, and it remains one of the most profound and disturbing findings in the history of science. Nobody knows what dark energy is. That's worth repeating. Nobody knows. It constitutes roughly 68% of the total energy content of the universe, making it by far the dominant component, and we have essentially no idea what it is or why it exists. The simplest model treats it as a cosmological constant, a uniform energy density inherent to empty space itself, which Einstein had originally introduced into his equations of general relativity in 1917, and then famously retracted, calling it his greatest blunder. It turns out Einstein's blunder might have been retracting the blunder. The cosmological constant fits the observational data remarkably well, but it offers no deeper explanation for where this energy comes from or why it has the particular value it does. Scholars still argue about whether dark energy is truly constant, or whether it might be changing slowly over time, a possibility that would have dramatic implications for the universe's future. A mainstream historical fact that connects dark energy to giant galaxies. The accelerating expansion has a direct effect on the growth of cosmic structure. As the universe expands faster, it becomes harder for gravity to pull matter together. Galaxy clusters, which formed when gravity overcame the expansion and collapsed pockets of matter into bound structures, will eventually stop growing because the expansion will carry potential new members away faster than gravity can reel them in. This means there's a cosmic deadline for galaxy growth. At some point in the future, no new galaxies will fall into existing clusters, no new mergers will occur, and the brightest cluster galaxies will stop getting bigger. The era of galactic cannibalism will end, not because the predators ran out of appetite, but because the prey was carried beyond reach by the expanding universe. For galaxies like IC 1101, this deadline is still billions of years away but approaching inexorably. IC 1101 will continue to consume nearby galaxies within the Abell 2029 cluster for a long time yet, growing slowly more massive as the cluster's remaining members spiral inward and merge. But eventually the cluster will run out of unmerged galaxies, and IC 1101 will sit alone at the centre, a single colossal elliptical containing all the stars that once belonged to hundreds of separate galaxies. This final state, sometimes called a fossil cluster, is the endgame of cluster evolution, and some examples of fossil clusters already exist. Ancient clusters where the merging process is nearly complete, and one dominant galaxy contains almost all the cluster's stellar mass. For Alcionius, the implications are different but equally profound. Its radio lobes are expanding into an intergalactic medium that is itself being stretched by cosmic expansion. As the universe expands, the gas between galaxies becomes even thinner, which in principle should make it easier for the lobes to grow. But the expansion also carries energy away, diluting the magnetic fields and relativistic electrons that make the lobes visible. Over time, the lobes will fade, their synchrotron emission weakening as the electrons lose energy and the magnetic fields diffuse. Eventually, millions or billions of years from now, Alcionius's lobes will become undetectable, ghost structures dispersing into the expanding void like smoke in an ever-widening room. The largest structure ever associated with a galaxy will dissolve into the background, leaving no visible trace that it ever existed. A quirky and somewhat melancholy implication of accelerating expansion. In the very far future, trillions of years from now, the universe will have expanded so much that galaxies outside our local gravitational group will have receded beyond the observable horizon. Their light will be redshifted to wavelengths longer than the observable universe itself, rendering them permanently invisible. A civilization arising in that distant epoch would see only its own galaxy, a single island of stars in an apparently empty universe, with no evidence that anything else exists or ever existed. The cosmic web, the galaxy clusters, the giant radio galaxies, all of it would be invisible, erased by expansion. Those future astronomers would face the same solipsistic cosmos that astronomers before Hubble assumed they lived in, a single galaxy floating in nothing, and they would have no way of knowing they were wrong. You feel something tighten in your chest at that thought, and then slowly release, because there's a strange comfort in it too. The universe is vast and temporary, and it will eventually erase its own grandeur. But right now, tonight, you know about it. You've seen the web, you've traced the filaments, you've visited the giants, and that knowledge, fragile and fleeting as it is, belongs to you. You've travelled a long way tonight. From your pillow, from the soft hum of whatever background noise is keeping you company, you have crossed distances that would take light itself millions of years to traverse. You started with your own galaxy, the Milky Way, that reliable 100,000 light-year disk of stars and dust and dark matter, and you watched it shrink. You watched it go from feeling like everything to feeling like a single grain of sand on a beach so wide you couldn't see the edges. You met IC-1101, that golden, ancient, bloated emperor sitting at the centre of its galaxy cluster, 6 million light-years of amber light, and 100 trillion stars burning quietly through the long afternoon of cosmic history. You descended into its core and hovered near a black hole so massive that crossing its event horizon would feel like nothing at all, just a gentle slide past an invisible boundary with no return. You imagined a planet deep inside that galaxy, a world where the night sky never goes dark, where constellations are impossible and darkness is a foreign language. And then you met Alcionius, the one that changed everything. 16 million light-years of radio lobes stretching outward from an ordinary galaxy, inflated by jets from a supermassive black hole that somehow punched far above its weight. You learned how it was found, hidden in data that had already been collected, waiting for someone patient enough to process the signals differently. You learned that its host galaxy is unremarkable, that its environment is probably sparse, that the intergalactic medium offered it a clear path outward the way a calm sea lets a ship sail farther than a stormy one. You learned that the cosmic web, the grand architecture of filaments and voids that organizes everything in the universe, may have given Alcionius the room it needed to become the largest structure ever associated with a galaxy. You toured the runners-up, Hercules A with its layered lobes and its rings of activity recorded like tree rings in cosmic wood. 3C236, the quiet former champion, Phoenix A, the anomaly where star formation refuses to stop and the cosmic thermostat appears to be broken, you saw that the universe produces these giants not through a single mechanism, but through a messy, variable combination of jet power and environmental conditions and cosmic timing, each one a unique experiment in how large a galaxy-related structure can grow. You confronted the limits of what we know. The square-kilometre array, still being built, promises to reveal radio structures fainter and larger than anything current telescopes can detect. The theoretical maximum size for a radio galaxy remains uncertain, bounded by the age of the universe and the density of the intergalactic medium, but not yet tested by observation. Something bigger than Alcionius might be out there. Something bigger almost certainly is, and you grappled with dark energy, the force that is pulling the universe apart at an accelerating rate, setting a deadline on the growth of galaxies and ensuring that the era of cosmic giants will eventually come to an end. Remember that moment, way back at the beginning, when you learned that astronomers in 1920 didn't even know other galaxies existed? Remember Shapley and Curtis standing in Washington, politely disagreeing about whether those fuzzy smudges were local gas clouds or distant island universes? Remember Hubble pointing his telescope at Andromeda and finding Cepheid variables that proved the universe was unimaginably larger than anyone had dared to believe? You have travelled the entire arc tonight, from that moment of ignorance to this moment of overwhelming, almost paralysing knowledge. You know things now that the smartest human beings alive a century ago could not have imagined. You know that your galaxy is one of 2 trillion. You know that some galaxies span millions of light years. You know that radio lobes can stretch 16 million light years across, and that the intergalactic medium, thin as it is, shapes the largest structures in the cosmos. You know that the universe is accelerating toward a future where all of this, every galaxy, every filament, every shimmering lobe of synchrotron radiation, will fade into cold, dark, unobservable silence. And somehow, lying here in the dark, that thought doesn't feel frightening. It feels quiet. It feels like the universe is exhaling after a very long day, slowly, gently, letting the tension of 13.8 billion years of expansion and collapse and merger and creation ease out of its shoulders. The galaxies will merge, the stars will burn out, the lobes will fade, and the silence that follows will be the deepest, softest, most complete silence imaginable. Not the silence of absence, the silence of completion. You are safe here. You are small, and that is not a flaw, it is a gift. Because smallness means you fit neatly into the spaces between the enormous things, and those spaces are warm and dark and perfectly sized for sleeping. The light from IC 1101 left its stars 1 billion years ago and has been travelling toward you ever since, crossing void after void after void, and tonight it arrives just in time to find you here, eyes closed, breathing slowly, exactly where you're supposed to be. Alcionius stretches its impossible arms across 16 million light-years of radio sky, and it doesn't know you exist, and that's fine, because you don't need it to know. You just needed to know about it, and now you do. The biggest galaxy ever discovered is out there, doing what it has always done, expanding slowly into the thinning dark, patient and vast and utterly unconcerned with the passage of time. And you are here, doing what you do best right now, which is letting go, letting the numbers dissolve, letting the distances blur, letting the soft golden glow of 100 trillion ancient stars fade gently into the warm darkness behind your eyelids. The universe will still be there in the morning, the giants will still be drifting, and you will wake up rested and small and miraculous a brief flicker of consciousness in a cosmos so large it needed 16 million light-years just to stretch its arms. Sleep well. The biggest galaxy in the universe is watching over absolutely nothing, and somehow that's the most comforting thought of all.